Our story begins in 1787, in the unassuming village of Ytterby, Sweden. Here, an amateur geologist named Carl Axel Arrhenius spent his days exploring a feldspar quarry. One afternoon, amidst the familiar granite and quartz, Arrhenius stumbled upon a heavy, black mineral unlike anything he had seen before. It shimmered with an unfamiliar, almost metallic luster, and its density hinted at a secret composition. He carefully extracted a sample, intrigued by this enigmatic find, little realizing that this dark rock held the key to an entire hidden world of elements that would one day redefine human civilization. Arrhenius named his discovery ytterbite, after its place of origin. For years, this unusual rock remained a curiosity, its true nature unknown. It sat in laboratories, a silent testament to the vast unknowns of the natural world. Scientists suspected it contained something new, but the analytical tools and techniques of the late 18th century were rudimentary. This wasn't just another mineral, it was a complex puzzle, waiting for the right mind, and the right moment, to unlock its secrets. Its dark, unassuming appearance belied a molecular tapestry of immense complexity. 7 years later, in 1794, the Finnish chemist Johann Gadaland took on the challenge. Working in his laboratory, he painstakingly analyzed a sample of ytterbite. His meticulous experiments revealed the presence of a new oxide, a fundamental component previously unknown to science. He named it yttria, and from this oxide, the element yttrium was eventually isolated. This marked the very first rare earth element ever identified, igniting a century-long quest that would slowly, element by element, unveil the full family of these unique metals from that single, black rock. The discovery of yttrium was just the beginning. The scientific community, now aware of ytterbite's hidden potential, intensified its research. In 1803, two prominent chemists working independently, Jöns Jacob Berzelius in Sweden and Wilhelm Hisinger in Finland, both successfully isolated another new element from a different mineral also found near Ytterby. They named it cerium, after the dwarf planet Ceres, which had been discovered just 2 years prior. This parallel discovery underscored the rich complexity hidden within these seemingly ordinary Scandinavian rocks. As the 19th century progressed, the challenge became clear: these elements were incredibly difficult to separate. They behaved so similarly that distinguishing them was a monumental task. Carl Gustav Mosander, a student of Berzelius, dedicated himself to this arduous process. In 1839, through meticulous fractional crystallization, he announced the discovery of two more elements, lanthanum and a substance he named didymium. Mosander's work was groundbreaking, pushing the boundaries of chemical analysis and paving the way for further revelations within this elusive group. Mosander's didymium was a particular enigma. Its name, meaning twin, reflected its chemical similarity to lanthanum. For decades, it was considered a single element. However, as analytical techniques improved, scientists began to suspect didymium itself was a mixture. It wasn't until 1879 that Marc de la Fontaine, a Swiss chemist, successfully isolated samarium from didymium, proving Mosander's twin was actually multiple distinct elements. This revelation highlighted the extraordinary challenge of identifying and separating what we now call the rare earth elements. The unraveling of the rare earth elements continued for almost another century. Each new discovery was a testament to human perseverance and ingenuity. Paul-Émile Lecoq de Boisbaudran, a French chemist, contributed significantly, isolating gadolinium in 1886 and then dysprosium. Much later, in 1907, Georges Urbain made the final discovery in this family by identifying lutetium. From that single black rock in Ytterby, a grand total of 17 distinct elements were eventually extracted, each with its own unique properties, slowly revealing their collective potential. Despite their name, rare earth elements are not actually rare in the Earth's crust. Elements like cerium are as abundant as copper. The rarity stems from two key factors: their diffuse distribution, meaning they are rarely found in concentrated, economically viable deposits, and crucially, their chemical similarity. They almost always occur together, making their separation an incredibly difficult and energy-intensive process. This challenge of separation, rather than scarcity, is what truly defines them and makes them so valuable. For much of the early 20th century, rare earth elements found their first major industrial application in gas mantles. When heated, a mesh infused with thorium and cerium produced a brilliant, steady light, far superior to traditional gas flames. This was a significant technological leap, illuminating homes and streets before widespread electricity. It was a tangible, if simple, demonstration of their unique properties and hinted at the transformative potential that lay dormant within these peculiar metals, slowly awaiting more complex applications. The 1960s marked a pivotal moment for rare earth elements, ushering them from obscure industrial uses into the homes of millions. The advent of color television demanded new phosphors capable of producing vivid, stable colors. It was europium and yttrium that provided the crucial red light, transforming grainy black and white images into a vibrant spectrum. This application not only brought rare earths into public awareness but also created the first significant surge in demand, proving their indispensability to consumer electronics and changing how we experienced media forever. Then came the 1980s, and with it, another revolutionary application: neodymium magnets. A powerful alloy combining neodymium, iron, and boron, these magnets were orders of magnitude stronger than any preceding magnetic material. Their incredible strength-to-weight ratio transformed industries. Suddenly, smaller, more efficient electric motors and generators became possible. This paved the way for miniaturized hard drives, compact speakers, and countless other devices, shrinking technology and boosting performance across the board. The world was about to be remagnetized. The impact of neodymium magnets extended far beyond consumer gadgets. They became foundational to the burgeoning green technology sector. Wind turbines, requiring highly efficient generators, rely on large quantities of neodymium to convert wind energy into electricity. Similarly, electric vehicles, with their need for powerful, compact, and efficient motors, became heavily dependent on these magnets. Without neodymium, the transition to a sustainable, electrified future would be significantly hampered, making it a cornerstone of modern environmental efforts. Today, rare earth elements are truly the invisible architects of our modern world. Your smartphone, with its vibrant display and tiny speakers, relies on europium, terbium, and neodymium. Defense systems, from precision-guided missiles to advanced radar, incorporate these elements for their unparalleled performance. Even the fluorescent lamps that illuminated our offices for decades, the CFLs, contain terbium, europium, and yttrium for their energy efficiency. Their reach is pervasive, underpinning almost every aspect of contemporary technology, from communication to national security. Yet, this ubiquity comes at a steep price. The extraction and processing of rare earth elements are notoriously environmentally intensive. The ore typically contains only tiny percentages of the desired elements, requiring vast amounts of rock to be processed. This involves strong acids, which generate toxic waste, and often results in radioactive byproducts, demanding careful waste management. The process also consumes significant energy and water, leaving a substantial ecological footprint. Balancing demand with environmental responsibility is a critical, ongoing challenge. Adding another layer of complexity is the geographic concentration of rare earth production. Since the 1990s, China has risen to dominate the global supply chain, controlling the vast majority of extraction, processing, and refining. This wasn't due to China having uniquely larger deposits, but rather a strategic decision to invest heavily in the infrastructure and accept the environmental costs that other nations were unwilling to bear. This consolidation of supply has profound geopolitical implications, creating significant supply chain vulnerabilities for the rest of the world. This dominance has thrust rare earth elements into the center of geopolitical tensions. Nations reliant on these materials for their advanced technologies and defense systems face potential supply chain disruptions and trade disputes. The strategic importance of rare earths has led to a global scramble for new sources, processing capabilities, and technological independence. Countries are now actively seeking to diversify their supply chains, invest in domestic production, and explore partnerships to mitigate the risks associated with such a concentrated market. Further complicating the future of rare earths is the challenge of recycling. While technologically possible, extracting these elements from end-of-life products like smartphones or electric vehicle batteries is often complex and economically unviable. The quantities in individual devices are small, and the cost of collection and processing often outweighs the value of the recovered elements. This means a vast amount of valuable material ends up in landfills, creating a linear consumption model that is unsustainable in the long term for our planet and our technological needs. The story of rare earth elements is far from over. Scientists and engineers are tirelessly working on solutions, developing new, more environmentally friendly extraction methods, exploring novel material designs that require fewer rare earths, and making strides in more efficient recycling technologies. The quest for alternative sources outside of China, from Australia to the United States, is also gaining momentum. The future demands innovation, collaboration, and a global commitment to responsible resource management to ensure these vital elements continue to power our progress. From a seemingly unremarkable black rock in a Swedish quarry in 1787, to the complex alloys powering our smartphones and electric vehicles today, the rare earth elements have traveled a remarkable journey. They are the invisible architects of our modern world, their presence often unnoticed, yet utterly indispensable. Their story is a testament to scientific perseverance, technological ingenuity, and the intricate web of global interdependence. As we navigate the challenges of the 21st century, understanding and responsibly managing these unique elements will be crucial for the future of humanity.